Okay, so lately we've been talking a lot about energy. We've talked about the different forms it can take, what an energy transformation is, and how it connects to the law of conservation of energy. We've also talked about the different types, kinetic, potential, and we've done some labs on it. So you worked on a solar cooker lab where one of the main energy transformations was from radiant to thermal. So now we're going to talk about what exactly thermal is. We're going to start with heat. Heat is the transfer of thermal energy from one object to another because of a temperature difference. So one object has to be colder or hotter than the other one. If they are the same temperature, heat does not happen. There's no transfer of thermal energy. And heat flows from hot objects to cold objects. So you think of that glass of water. You can tell it's cold when you touch it. The reason you can tell that is because the heat is actually transferring, flowing from your hand to that colder glass of water. When the heat is leaving your hand, you feel that as cold. Another example would be when you touch a hot stove. If you accidentally put your hand down, you immediately know that because the heat is flowing from the stove into your hand. It never goes from cold objects to hot, always hot to cold. The next thing we want to talk about is temperature. So you hear a lot about temperature in weather forecasts, but do you actually know what it is? Temperature is the measure of how hot or cold an object is compared to a reference point. Depending on which unit of temperature you are using, those reference points are different. So when we talk about degrees Celsius, the reference point is water. So we know that water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. So they use that 0 to 100 based off water. Fahrenheit now actually uses common temperatures people experience in their climate. Ranging from 0 to 100, those would be common temperatures that people might feel outside. Hopefully we don't get to 0 anytime soon. Temperature is a measure of the average kinetic energy of all the particles in an object. So if you think back, we talked about the kinetic theory. Kinetic theory tells us that every particle in an object is always moving, whether it's bouncing off the walls like in a gas or just vibrating in place like in a solid. They're constantly moving. So temperature tells us the average kinetic energy. Okay? So it tells us basically how fast those particles are moving. That's what temperature actually measures. Where temperature is measuring the average kinetic energy, so only the movement, thermal energy is the total potential and kinetic energy of all of the particles in an object. Thermal energy, therefore, depends on the mass, so the size of an object, how much space it takes up. It depends on the temperature, so how the average kinetic energy of all those particles, how quickly they might be moving, and the phase of an object. So if it's a solid, liquid, gas, plasma, any of those that we previously talked about. So because thermal energy depends on the mass, that means there will be more thermal energy found in a pot of hot water than in a glass of hot water because it contains more particles. So if there are more particles, there's going to be more energy. Next thing we want to talk about is thermal expansion, and I'm sure all of you have experienced this. So thermal expansion is when a substance expands as it gets hotter because the particles move faster and farther apart. So as things get hotter, they start to expand, they start to move faster, all of them are moving faster, and that means they're going to get farther and farther apart. One example of this would be in the summer, if you have a wooden door, it gets really hard to open and close that door. Those particles in the wood are starting to expand, they get bigger, and then it makes it hard to close the door. It's not going to fit in that frame as well. Another example of this would be if you wear rings. Sometimes certain rings start to get a little tighter in the summer because the particles in your skin are starting to expand as well. Try to think of another example if you can. Write that down on your sheet. The next one would be thermal contraction. So that's just the opposite of thermal expansion. So thermal contraction is when a substance gets smaller as it gets colder because the particles move slower and get closer together. So in a way, it's kind of like they're getting colder, so they're getting closer together to huddle to keep warm. You can think of it that way. Another example of this would be, again, that ring. Right now it's getting colder and colder outside, so my wedding ring's starting to slip off. It's a little bit too easy to take off. That's one example. Another example would be if you've ever had a helium balloon. If you take it outside in the winter, it really shrinks up. It contracts. It gets a lot smaller, and you start to see all the wrinkles in the balloon. If you bring it back inside, where it's nice and warm, those particles are going to expand back out, and the balloon is going to be back to normal. Again, try to think of another example if you can, and write that down on your sheet. We'll go over it in class when I see you guys. The last thing that we're going to talk about is specific heat. So this is actually the amount of heat needed to raise 1 gram of a substance 1 degree Celsius. So that's important to remember, we're measuring in Celsius right now. So 1 gram, 1 degree Celsius, that's specific heat. The lower the specific heat, the faster something gets hot. So if we're looking at an example, copper and wood, we have copper specific heat at 0.385. So that's fairly low. Wood specific heat is 2.50. So which one of those would heat up faster? The answer is copper. Copper is going to heat up faster. It's a better conductor of heat. So we're going to be doing some more practice with that when we get to it. And that's it for today. So it was a relatively short video. Make sure you jot down your notes. If you need to go back, rewind, go ahead. Watch this as many times as you need. Use it as a study tool. Whatever you need to do so that you get an A. All right. Bye.